purely on engineering, energy conversion, material science, and operational metrics of humanoid robots. The numerical juxtaposition, a human benchmark of 2.45 meters against a robotic achievement of 2.88 for 3 meters, offers a compelling case study in mechanical efficiency. To the layperson, this difference represents a victory of strength. To the engineer, it represents a definitive triumph of systemic efficiency. When we strip away the spectacle of competition and examine the robot's performance through a purely technological lens, the 0.4343 meter gain is not merely an athletic upset, but a profound demonstration of how modern mechatronics optimizes the conversion of energy, the utilization of materials, and the precision of control. This essay posits that the humanoid robot's performance is a masterclass in 3 critical pillars of technological efficiency: thermodynamic energy conversion, structural hysteresis minimization, and algorithmic control precision. Let's see the energy conversion efficiency. At its core, any jump, whether biological or mechanical, is an exercise in converting stored potential energy into kinetic energy to overcome gravitational pull. The human musculoskeletal system operates at a notoriously low thermodynamic efficiency. Human skeletal muscles convert chemical energy, ATP, into mechanical work at an average efficiency of approximately 18% to 25%. The remaining 75% to 82% is dissipated as thermal energy, or heat. This waste necessitates complex, heavy, and energy-draining evaporative cooling systems, sweating and increased respiration, which add parasitic mass and further reduce the net work output per unit of fuel consumed. In stark contrast, the electric drivetrain of a humanoid robot, typically composed of brushless DC motors and advanced lithium polymer battery cells, operates at an energy conversion efficiency frequently exceeding 90%. The electromechanical coupling in these motors suffers minimal resistive losses, I²L losses, when optimized with high-quality copper windings and rare earth magnets. For the robot to achieve 2.88 for 3 meters, it must generate a specific takeoff velocity, a v equals square root 2gh, almost equal to 7.52 meters per second. Given the mass of a humanoid robot, often tilde 70 kg for bipedal units, the required kinetic energy at takeoff is roughly 1.98 kilojoules. For a human, generating this energy requires expending nearly 8 kilojoules of metabolic energy, a grossly inefficient process. The robot, however, expends only tilde 2.2 kJ of electrical energy to produce the same output. This tilde for X improvement in energy efficiency means the robot generates significantly more ballistic work per watt-hour, allowing it to outperform the human record while theoretically consuming fewer input resources. The technological efficiency here is not about raw power, but about the fidelity of energy transfer. Let's see the defeat of hysteresis and material waste. The second dimension of efficiency is mechanical, specifically, the efficiency of the structural chassis and kinetic chain. Biological tissues suffer from inherent hysteresis. Human tendons, while possessing an admirable elastic recoil, returning roughly 70 to 80% of stored energy during the stretch-shortening cycle, are still prone to viscoelastic energy loss. Much of the force generated during the counter-movement phase of a standing jump is wasted as internal friction within muscle fibers and joint cartilage. Technological materials transcend this biological limitation. Advanced humanoid robots utilize carbon fiber-reinforced polymers and spring steel actuators that exhibit exceptionally low hysteresis, boasting energy return rates exceeding 95%. The structural integrity of the robotic chassis ensures zero parasitic flexion during the eccentric loading phase. When the robot's actuators engage, the force is channeled through rigid exoskeletal components directly to the ground with minimal torsional deformation. This is the essence of mechanical efficiency, the maximization of output work relative to input strain. The robot achieved 2.88 for 3 meters, almost 3 meters. This proximity to a round metric threshold is indicative of an engineering team that optimized for maximum vertical displacement given the finite torque limits of the joints. By utilizing lightweight alloys with a superior strength-to-weight ratio, e.g., titanium or aerospace, Grade aluminum, the robot reduces the gravitational load it must lift, effectively increasing the efficiency of its power-to-weight ratio. The robot is not burdened by excessive water weight or non-contractile tissue, allowing it to allocate 100% of its structural mass to force production. Algorithmic precision, the efficiency of zero wasted motion. Perhaps the most profound efficiency lies not in the hardware, but in the software. The human neuromuscular system relies on stochastic, probabilistic firing patterns to coordinate a jump. This results in significant energy leakage through lateral sway, torso over-rotation, and suboptimal joint angle sequencing. A considerable portion of the energy generated by human muscles is dissipated as heat and sound due to this kinematic inefficiency. The robot, by contrast, leverages advanced model predictive control, MPC, and inverse kinematics. The algorithmic efficiency is visually evidenced by the precision of the output metric, 2.88 for 3 meters. This for decimal place precision is the hallmark of a closed-loop control system operating at kilohertz frequencies. The robot's onboard inertial measurement units, AMUs, and joint torque sensors provide instantaneous feedback, allowing the microprocessor to calculate the optimal joint trajectory in real time. This computational efficiency eliminates non-essential micro-movements, often referred to as jitter, which plague human athletes. Every milliampere of current drawn from the battery is rigorously directed along the optimal vector of force. There is no energy lost to counterproductive oscillations. The control algorithm ensures that the actuators fire in perfect synchronicity, achieving a superposition of joint torques that maximizes the net impulse applied to the ground. The technological efficiency here is defined by the reduction of entropy in motion. The robot's leap is a deterministic, mathematically pure trajectory, whereas the human leap is a chaotic, dissipative event. Operational and temporal efficiency, repeatability without degradation. Finally, a critical assessment of technological efficiency must include the dimension of time and consistency. Human performance is characterized by a sharp performance degradation curve. A single maximum effort standing jump depletes phosphocreatine stores, floods the muscles with lactic acid, and induces microscopic tissue damage, rendering a repeat performance significantly lower in height. Technological efficiency, however, is defined by repeatability without fatigue. The robot that produced the 2.88 for 3 meter result can theoretically execute this precise leap thousands of times with negligible variance, limited only by battery state of charge. This operational efficiency means the robot's mechanical components undergo zero structural fatigue during the jump cycle, and the cooling systems, phase change or forced convection, effectively manage the minimal thermal buildup. The input energy required for the second jump is identical to the first, indicating a linear, highly efficient operational model. The human record of 2.45 meters is a fleeting, singular peak. The robot's 2.88 for 3 meters is a stable baseline, showcasing that technological efficiency excels not just in peak output, but in the consistency of that output over time. The leap from 2.45 meters to 2.88 for 3 meters is not a story of human obsolescence, but of engineering optimization. Analyzing of superior thermodynamic conversion, 90% versus 25%, superior structural energy return, 95% versus 70%, and superior algorithmic motion control, zero stochastic energy leakage. The robot's achievement is a testament to the power of marginal gains achieved through material science and cybernetics. It demonstrates that the true potential of humanoid robotics lies not in mimicking the human form, but in perfecting the physics of motion, extracting the maximum possible mechanical work from every joule of electrical energy, every gram of structural mass, and every millisecond of computational time. In this context, the height of 2.88 for 3 meters is merely a byproduct. The real, enduring record is the sheer, breathtaking efficiency of the mechanism that produced it.